I'm Braden Barbary, and this is my presentation over my lab 1, which was about constant velocity. This lab is focused on Newton's second law, which states that an object with no net force acting on it will stay at a constant velocity. The formula here is the backbone of his law, and I will go into more detail about it later. To find the position of the object in the example, tracker and glow script were both used and gave me data that I will show you later on in the presentation. For this experiment, an object was rolled across a table, and the rolling object was the system, and then the table acted as the surroundings. And at the end, it was found that Newton's second law was able to predict the placement of the object. So for the testing, tracker was used to observe the object's position relative to the time, and it was done by placing individual points at the center of the object for every frame to track the movement. And then in this video, which is of the object rolling, it was tracked. And then in the background you can see a meter stick here, and this was used to find the distance that the object rolled. Another important part was the coding, and this was able to create a simulation of the object's position relative to the time using glow script. And here is the actual code. As you can see, the velocity of the ball equals 0.655. I inputted this, and I found this number by using the formula the change in position divided by the change in time. So I took 2 points of the object rolling, and I subtracted the second position minus the first position, and then divided it by the second time minus the first time. And this was able to find the average velocity. Another important part was that the net force on the object was 0. And this 0 net force is needed for this equation because it gives that the ball's velocity equals the ball's velocity plus F net divided by mass times delta t. But the velocity will not change here if F net is 0 because this whole part goes away, and then you're just left with ball's velocity equals ball's velocity. Another important thing was the ball's position, and this formula was given by ball's position equals ball's position plus ball velocity times delta t, and this was given by the ball's velocity, which was found earlier, and then multiplying it by the time intervals to update the thing. And these two formulas combined can create the first formula that I showed you earlier. Here is the output given by both the tracker and the code. As you can see, they're very similar with small variations as you follow this tracker line, and that would be due to human error throughout the clicking. And there is no variation with the code, it is just an exact value. And if you were to change the positive x-axis to a negative x-axis for both of these graphs, it would give the same magnitude of slope, but it would be a negative value. And for this lab to work, some assumptions had to be made. The first one is that there will be no friction on the object. Now this is not true in practice, but for Newton's formula that I showed originally to work, there has to be no friction on the object. And because it's such a small time interval, it can be assumed that the friction will have a very small effect, so the formula still is able to very accurately depict the position. Another assumption is that the force pushing the object down is the same as the force pushing the object up, and since it is a flat table, this should be true, and if there was slight curve or slight slope on the table, it would be so small it also can be ignored. So in conclusion, Newton's formula was able to predict the motion better than just watching the object, but if you're going to put this on a larger scale, it will become worse because the friction force on it will grow, and it will change it more and more the larger the scale gets. Thank you for listening to my presentation.